Lecture 18 covers sections 6.2.4 through 6.2.5. At the end of today's lecture, you should be able to calculate strain due to applied loading, as well as the strain due to thermal effects, and how to convert these two strains into axial deformation. Now let us pose the concept of thermal expansion, and we can ask ourselves, why are bridges designed with a gap between the plates, i.e. an expansion gap? Well, all materials have a coefficient of thermal expansion. This is known as alpha. And alpha is on the order of 1 to 200 with units of 10 to minus 6 meter per meter degree C. Now, alpha quantifies how a change of temperature of a material causes a change in the material size. Notice the R unit is really on a per degree C basis. Now, for a bridge, our coefficient of thermal expansion of concrete is approximately 13.5, and that of steel is approximately 11.7. Now note the unit. Now, if we consider a seasonal temperature change in Minneapolis of approximately 34 degrees centigrade, the concrete and steel can expand and contract an appreciable amount, on the order of tenths of millimeters per unit length. Now, the thermal strain due to a temperature change, which is defined as delta T, is defined as epsilon sub T is equal to alpha delta T. Now notice alpha had units of 1 per degree centigrade, and delta T has units of degree centigrade. Thus, our thermal strain is dimensionless. The T subscript lets us know it's thermal. Thus, the total strain on the system is due to our applied load and change of temperature, each of which is independent of one another. And we can express strain as our strain due to our stress, i.e. epsilon sub sigma, plus our thermal strain, i.e. epsilon sub T, which is equal to sigma per E plus alpha delta T. Now, we recall strain is deformation per unit length. We can rearrange this expression to solve for deformation. That is, our deformation delta is equal to our strain epsilon times our length L. Now, when a uniform member is loaded axially, the deformation at the end of the bar can be expressed in terms of strain and the initial characteristic length. Now, if we recall the modulus of elasticity, where E is a rise per R run in the linear elastic region on our stress strain curve, we can say delta is equal to sigma L per E. For an axially loaded member, sigma is simply the force per unit area. Thus, our deformation is expressed as RL per EA, where R is our internal reactionary force, L is our length, E is our modulus of elasticity, and A is our cross-sectional area. Now, recalling there are two independent forms of strain, both are thermal and stress-induced. We can express our total deformation equation as follows. Delta total is equal to our deformation due to our thermal effects plus our deformation due to our applied loads. And we can say this is equal to alpha delta T L, which is our deformation due to our thermal effects, plus RL per EA, our deformation due to our applied loads. Now, if there are multiple members with different cross-sectional areas, different lengths, different applied loads, or different moduli of elasticity, the deformation is the sum of each individual deformation of each unique configuration. And this would be equal to sum from I is equal to 1 to n of R sub I, L sub I, per E sub I, A sub I.